In this video, we're going to explore kind of the implications of different step sizes on how fast the gradient descent algorithm actually converges to a minima. So in particular, we're going to try to explore how we can find the best step size for each individual iteration that we perform. So remember that in class, we talked about how we can use gradient descent with a constant step size. So what that really entailed was when we're moving towards our better guess, we stepped a very specific kind of amount in the direction of the negative gradient each kind of iteration. And that step size remained constant throughout the entire iterative process. And the algorithm for that, we basically just have to do the usual kind of kit and caboodle for optimization schemes. Find an initial guess, initialize an error, initial set a iteration tolerance, and all of that jazz. And in particular, we pretty much just update using the gradient descent algorithm. The only difference here is our step size that we talked about, we're remaining constant. So let's just kind of get a picture of what that looks like. So we're just going to find a minima of this function. That's basically just a linear combinations of a sine and a cosine. But here's what the iteration looks like. So we take off, we start moving towards that minima. We're taking a fair amount of steps. Even once we get close to that minima, it's taking a while until we actually converge there. Now, it looks like we're not moving slightly, but that's just because the error tolerance is so small. In this particular case, it's a 10 to the minus 4 accuracy. And it took us about 13 steps, which honestly is not bad for this 2D problem. But you might imagine if we're in the real world where we have a problem of hundreds or even thousands of variables, and we're trying to do some type of global minimization or even finding local minima, each iteration might be very costly to compute. So we ideally want to kind of minimize the amount of iterations we are also doing in this minimization problem itself. So how can we actually go about and do that? And well, that takes us to the next kind of thing where what if we want the step size itself to change each iteration? So this would be like saying, what is the best step size for the first iteration? What's the best step size for the second? And so on and so forth. And now the algorithm itself doesn't change too much. Besides, we get to do a couple different things. So in this case, again, we're trying to find the best step size in each iteration itself. So we're finding the best gamma for each iteration. And there's a couple new things we get to do. Well, the first thing, we need to initialize some step size, basically just as an initial guess of what the first best step size is. So there's that kind of initialization. But then also in the iterative process itself, we need to keep coming up with better or with the best step size in each iteration. Every time we go through that while loop, we find a better gamma or the best gamma value for that particular round. So what does that actually look like? So just to bring us full circle, or just to bring us back together, remember we are doing a minimization problem, which is why we're doing gradient descent. But on top of that, we're now trying to ask this other problem of how can we minimize the number of iterations that we need to do for gradient descent. So we're doing a minimization problem of a minimization problem, kind of. But we're going to basically tackle this question right now of how can we find the next best step size? So let's bring this down and maybe solidify this problem a little more. So let's look at a specific example now. So instead of considering kind of a function from n variables into just R1, well, let's just consider R2 going to R1 for our function. And this will just be a function of minus sine x minus cosine y. We're trying to minimize that over all x and y. I'm going to use gradient descent to do that. And we want to try to figure out what the best step size is each iteration in hopes that we only have to do far fewer iterations to actually converge. So what does this actually look like then? How can we calculate the best step size each time we go through that while loop? So we're really asking this question now of how can we find a gamma value that minimizes our function even further? So this function is what we're trying to minimize with our iteration every single time we go through it. So let's just kind of make sure we're all on the same page here. So this specific example, like I said, on the left-hand side of the screen, we're going to consider the function minus sine of x minus cosine of y. Just something with lots of local minima, local maxima, and things like that in it. All right, so our function that we're really considering, again, another way we could write this is, again, f of x, where x is now a vector. The vector has two components, x and y. Okay. But what are we actually doing here for this minimization problem, trying to find the best gamma? So we want to try and find, again, gamma that minimizes this function. Let's bring this down to earth a little more. So if we just, consider our normal finding the gradient of a function. In this case, since the function just gives us back one bit of information, as in we're going R2 to R1, we just have two partial derivatives, df dx and df dy, both partials, of course. And that gradient vector just gives us minus cosine of x, and then a positive sine of y in that second component. So those are our functions, or the partial derivatives, with respect to x and with respect to y. Now, the reason I want to go through this is the first thing we need to consider is basically when we're at the nth iteration, we know what the previous guess was. As in, we know what the xn guess was. So we have basically at our disposal the components xn and yn of the previous guess vector for our solution. So that's one bit of information. And why this is useful is, well, if we circle back to the top here, the only unknown then in which we're evaluating that function is the unknown that we're after, that gamma n. So since xn, we already know. We know those x and y values. They're just whatever approximation happened at the nth guess. So on that note, let's try to write out how this is actually just a function of gamma itself. So in doing this, I just want to be very clear. So let's start just kind of highlighting things. This might seem a bit goofy, but I think it'll help us keep track of everything we're about to do. So the x's I'll just highlight with one color, the y's I'll highlight with another color. So if we look at the function that we're evaluating, as in we look at this as a vector evaluation, well, when we write this function again, we're basically writing this as x component n minus our unknown gamma n times the gradient in the first component. So just, oops, not the eraser, partial f, partial x, evaluated at xn, yn. That's the first component that we're putting into the x place. In the y place, we're putting yn minus gamma n. Again, that's the unknown we're solving for. Partial f, partial y, evaluated at that previous guess, xn, yn. So this looks like a mess. I'll just try to highlight again what our unknown is here. Our unknown, of course, is, well, that gamma n. But everything else in this function, we know. We can actually just go ahead and plug these into, well, how we normally plug our stuff into a function. So we have sine, or minus sine, excuse me, of basically everything in the x component. So that'll be xn minus gamma n times partial f, partial x, which we saw up above was minus cosine x. And then the next piece that we do, we substitute in, well, the y stuff in for where the y is happening in that cosine term. So we have minus cosine of y, or the information in the yth component, very much again, a composition of functions. So we have yn minus gamma n, and then times partial f, partial y, which in this case is just, well, sine of y. Let me keep up with the color scheme. And I just noticed there's one little mistake. Basically, when I wrote that minus cosine of x, I need that to be a cosine of xn. So hopefully that was clear of how we basically took our function as a composition of functions, you can think of it. We took what we're substituting in the x spot, which was that, and we're just putting it in for x. And the next part we did was, we'll just take what's in the y spot and put it in everywhere we see a y in that equation. And now again, the important thing for us to recognize here, the only actual unknown are these gammas. Since we assume we know the nth approximation for our solution, as so we know xn vector, again, we know xn and yn. So the only thing that's a variable in that last function then is just that gamma. So the problem that we actually need to find again is we're minimizing with respect to gamma of the function minus sine xn minus gamma, which I'll just, that minus cosine gives a plus cosine of xn, minus cosine of yn minus gamma n of sine n. And again, the only unknown in this case is that gamma term. So that is what we actually want to minimize. We could write that, that's clearly just a function of gamma now, since xn and yn are some known approximation values. So rather than kind of write this in this more abstract way, first what I want to do is just define a function g of gamma. Just to make it explicitly clear that what we have is just a function of one variable. It's just this gamma sub n. The xn, yn again are approximation values that we know. So the problem that we're really looking for, and this will just be the restatement of what I wrote just with our definition of the function g, we're really trying to minimize this function g just with respect to the unknown gamma n, the step size for our gradient descent. So we did a lot of composition of functions just to basically substitute in and make it clear that we're really doing a minimization problem over just the step size gamma. So we have some options now that we have this. How can we minimize this function that's a function of gamma now? And well, we could do something like a Newton's method. Remember, for Newton's method, basically what we would get in this case is, well, we would just keep churning out better and better guesses. So let me just kind of write what we have now. And define some things. So this gamma sub n, raised or superscript j, that's sort of the jth guess at what this gamma would be. So this is how we're churning out better and better gamma approximations just in this particular step of gradient descent. But then Newton's method basically says, well, for a 1D function, if I'm doing this for optimization, I want to find when the derivative of that function is equal to 0. So let's just be clear, we're doing Newton's method for optimization. And since the function that we have is g sub or g of gamma n, we want to find basically when g prime of gamma is 0. So I'll just write that out. So because of that, well, when we do this for Newton's method, we need to take, well, the derivative of that function g and evaluate it at our current guess of what that gamma value might be. But then we divide by, well, its next higher derivative, which is g double prime. And again, we evaluate that at the jth guess for what that value of gamma should be. So this is what this would look like if we're doing an optimization problem to figure out what the best gamma is. We have our function g that we set up. That's the function we're trying to minimize with respect to gamma sub n. And where that function came from was really just saying, you know what, we want to figure out what the lowest possible next guess we can get from gradient descent was. So we start off with basically this question of how can we minimize what we want coming from gradient descent. We're trying to minimize this function f. So what we're really asking is, at the next gradient descent, how can we minimize it even further? So what we need to figure out now, what's left is basically, well, we need to compute a derivative of g, and we also need to compute its second derivative as well. Remember, these are with respect to gamma, not xn or yn, because those quantities are known. Those are just whatever the nth approximation was, xn and yn. So we have this function essentially, g of gamma. Just copy down what we had before. And for right now, I'm just going to get rid of the sup or subscript on the gamma. We really just, these are functions of gamma, or g is just a function of gamma. So we compute g prime. We are taking derivatives with respect to gamma, not xn or yn. So in this case, we get to do a bit of chain rule stuff. First, take the derivative of minus sine. That'll give us minus cosine of everything inside. But then from chain rule, we get to differentiate that inside portion. So when we differentiate that inside portion, we just get the derivative of gamma times cosine. And well, that just gives us a cosine. Now we do the other term, take a derivative of that minus cosine thing. We start from the outside in doing chain rule. So derivative of minus cosine gives us a positive sign. And again, we get positive sign of everything that's there. So yn minus gamma times sine of yn. And that is our, and then of course, well, we need to take the derivative of, well, what's inside by chain rule. And again, gamma is our variable here. So gamma times sine, we have to differentiate, take a derivative of it, we get minus sine. Since that minus sign is sitting in front of the minus gamma sine term. And we can do the same exact thing over again, just to find the second derivative. And actually, it doesn't change too much. The chain rule isn't that scary, actually, because the inside of that cosine and inside a sine are just basically linear in gamma. So taking a derivative of minus cosine times cosine Well, the gamma is only in that first cosine, so we actually only have to worry about that first piece. So we get a derivative minus cosine, gives us a positive sign of everything inside there. And then, of course, by chain rule, we get to differentiate, well, what's inside. So differentiating what's inside that cosine, again, we just have that plus gamma cosine. So we just get another factor of cosine. That'll multiply that factor that's already there. So we have basically a cosine squared xn sitting outside. All right, next, move to the next term. Well, the only gamma is inside that first sign, so we don't have to worry about that second sign, negative sign yn really. So differentiating that minus sign, or sorry, that positive sign, we get a cosine term. So we have plus cosine, and we get yn minus gamma sine yn. But then, of course, we differentiate what's inside by chain rule. We differentiate what's inside that we just have to worry about the minus gamma sine term. Differentiating that, we get another factor of minus sine yn. So we actually just get that multiplying a positive sine yn at the end of the day. So we can compute all the derivatives we need of that function g. So then we can just go ahead and perform a Newton's method to actually find the best gamma for each individual step. So if we take a look at what this looks like, again, that is the function that we're looking at. It's just something with lots of local min, local max. And well, here's what Newton's method looks like. We take a big step, and we basically get right there at that minimum. So for 10 to the minus 4 accuracy, it only took our Newton's method 4 steps, which was, 3 times faster than what it took that constant gamma value. And of course, you could ask, well, there might be better constant gamma values to try. So you can test that, test out a lot of things. But if you're trying out lots of constants of gamma, again, in a real world practical sense, if we're dealing with a function of hundreds or thousands of variables, that's just not feasible to find what the best gamma value is for your problem if you have to just test your minimization scheme, say 10, 20 times of just different gamma values to try and field it out. So Newton's method really seems to be a lot better in this case. And in fact, if we do the same problem and just compare basically all of our methods so far, so constant gamma, the Barlazai-Borwein step, and our Newton's method, we can see that, well, to achieve 10 to the minus 10 accuracy for a minimization scheme, it took our constant gamma about 33 iterations. Our Barlazai-Borwein, I spelled the one name wrong, I apologize, took us 8 steps, but then our Newton's method, it only took us 4. So Newton's method really is reducing the amount of iterations necessary to find some of these minima. Now, of course, Newton's method, like we discussed in class prior, can come with lots of issues. So what do I mean by that? Well, for example, if I try just another case with Newton's, trying another initial guess, this time we're trying from the bottom left, and well, we're actually converging now, not to a minima. Even though we're using gradient descent, we're converging to a maxima. It's because Newton's method is changing the sign of that step rather than always minus gamma gradient. Our step size is negative, so it looks like we're going plus gradient in that case. The other part of this is what can happen with Newton's method sometimes is it just might not converge. So for example, here's another case. Our Newton's method actually heads towards a saddle point and actually just doesn't converge when we're getting, or when our gradient descent is moving towards a saddle point now. So again, this is another kind of finicky aspect of what's coming from Newton's method. So I hope this video helped kind of sort it out. Again, the big thing to remember is when these methods work, we find the best step size for a particular iteration of gradient descent. It can really reduce the amount of iterations that we are necessary to achieve a specific tolerance. But sometimes we can run into issues of we don't converge to a minima, we converge to a maxima. We don't even converge at all. Newton's method to find the best step size just has some problems. So we have a bunch of options. We can go with the constant gamma, we can go with the Barzilai-Borwein step, or we can try to find this optimization scheme, and maybe not instead of using Newton's method, we use something else like a golden section search to find the best step size.